let's take a look at how we use vectors to solve geometry proofs. Now, keep in mind these things. When you've got a shape, it's a good idea to pick one of the vertices, let it be let it represent the origin. It doesn't have to be a vertex, of course, it could be another key point, but some reference point in your object. Sum or difference of vectors will create a triangle. So in other words, when you've got two vectors coming from one point, you know the vector joining them would be the third side of a triangle, which we saw was going to be the difference of the two vectors, so head minus tail. Parallel vectors will be multiples or scalar multiples of each other. We can use the dot product if we need to find the angle in a particular shape. And that one's very useful because in a lot of geometry proofs we're trying to show things are perpendicular and things like that, and that's when our dot product will equal 0. As I just said before, you can always write any vector as head minus tail. Okay, so let's do a few. We're going to prove the diagonals of a rhombus are perpendicular. Now, when we're proving using vectors, it's not good enough to simply say, oh, the length of this side is the magnitude of this vector. And that's not really using vectors, it's just writing a pronumeral in a different way. So I actually want you to use vector ideas. Diagonals of a rhombus are perpendicular. Well, let's draw up a rhombus. So OABC, so I've labelled one of the vertices O, that's going to be my reference point. And from that reference point, there are two vectors coming out. So I'll call one of them A and one of them C. Now the diagonals are OB and AC, but they form the third side of triangles. And in fact, we know in a parallelogram that one diagonal, in this case OB, will be the sum of the two vectors, A plus C, and the other diagonal will be the difference. Now I've called mine C minus A, but I could have just easily have called it A minus C. It just depends which direction I've got the vector going. Okay, we're trying to show those diagonals are perpendicular. So if we're talking about vectors, I want to show the dot product of those two vectors are equal to 0. So A plus C dot C minus A. Well, that's the difference of two squares. So C dot C minus A dot A, which becomes magnitude of C squared minus the magnitude of A squared. So it is the difference of two squares, but remember, it's the magnitude of the vector squared, not the vector that's squared. Well, the other thing we know is that the magnitude of A must be the magnitude of C, because our starting point was this is a rhombus, and we know sides in a rhombus are equal. So those vectors must have the same magnitude. Well, if that's the case, my dot product must equal 0. Well, therefore, they must be perpendicular. I'm just calling it OB the diagonal rather than the vector, but it doesn't really matter in this case. I'm simply saying these two lines are perpendicular. Let's prove Pythagoras' theorem. So right angled triangle, seems logical to make the right angle my reference point. So I've called that one O. And two vectors coming from O, so I'll call one of them A, I'll call one of them B. Our diagonal then will be head minus tail, and the direction I've put it, it'll be B minus A. Well, let's work out what OA squared, so that's the length OA squared, not the vector OA squared. So let's find OA squared plus OB squared. Well, OA squared would be the magnitude of the vector A squared plus the magnitude of the vector B squared. Okay, let's have a look at AB squared. So that would be the magnitude of B minus A squared. So we expand it out by saying, oh, well, remember we know that squared is like that vector dot itself. So in this case, B minus A dot B minus A. We can expand that out, but remember we're not multiplying, it's the dot product, so it's B dot B minus 2 A dot B plus A dot A. But B dot B and A dot A we know will be the magnitude squared and so on. But the other thing we know, we said this was a right angled triangle. So OA I know is perpendicular to OB, therefore the dot product of A and B must be 0. So subbing that all in, I get B dot B plus A dot A, which is magnitude of B squared, plus magnitude of A squared. Oh look, it's the same thing. Therefore, Pythagoras' theorem is satisfied. ABCD is a quadrilateral. Now this time the shape was given to me. So there's not one labelled O, which I can conveniently call the origin. I'll just make something my reference point in this. What are we told? RP, Q and S, they're the midpoints of those different lengths. What type of quadrilateral? So if we were to draw up P, R, Q and S, what would we get? Okay, I'm going to treat A as my reference point, my origin, if you like. Coming from A, I've got AB, so I'll just call that the vector U. AC is coming from there as well, so I'll call that V. AD is W. All right, but I now want to try and write everything else in terms of those three. So AP, which is half of AC, so I know that will be a half V, so I've got that one. BQ, well, BQ would be half of BD. I haven't got BD, but BD would be head minus tail, but because I'm calling it BD, that means it's W minus U. AR, done that one as well. Well, that's half of the vector AD, so half of W. BS, done that one as well. Half of AC, so half of V minus U, head minus tail. Look, I might not end up using all of these. I'm just listing all the different ones, seeing what will happen. So it's the quadrilateral RPQS. So let's investigate those sides of the quadrilaterals, although it's a vector. PR. How can I get PR with things I already know? Well, remember we can get PA and AR and smash them together if you like. That would get PR. Now PA, well, that'll be the negative of AP, so that's minus a half V. AR, yep, we've got that one. That's half of W, so it's a half W minus V. So I've got an expression for PR. Now, SQ. Well, SQ, again, I could smash together SB and BQ. Have I got those ones? Well, I've got BS, so SB would be the negative of that, so half of U minus V. BQ, yep, there it is. That's going to be half of W minus U. Adding those together, we get a half of WR minus V. Look at that. It's the same as PR. Therefore, they are equal vectors. Well, if they're equal vectors, then their magnitude must be the same, but their direction must be the same as well. So we've got a parallelogram, because we've got a pair of opposite sides that are both equal and parallel. So we know it's a parallelogram. This one came from last year's HSC, so give you an idea of what they're looking for here. They gave us a very out of scale diagram if you look at it, because they're telling us that BD, the length of that vector, is the same as the length of AC, and clearly in the diagram they're not. Possibly that's so we don't start assuming things or something like that. But what else have they told us? Well, they've told us the two parallel sides in the trapezium. That's pretty much it. They've forced our hand by telling us to let AB be A, BC be B, but AD is going to be some scalar multiple of BC. Well, that makes sense because they're parallel, they're going in the same direction, but they say, well, their lengths are different, so one will be a multiple of the other. They want us to show this wonderful expression, 2 times A dot B plus 1 minus K times the magnitude of B squared is equal to 0. Now, I'm sure you're just looking at that shape and go, well, that's obvious, of course it is. Right, what is the significance of that? I have no idea what the significance of this result is, but they just want us to show it. Okay, well, let's start finding some things now. It seems to make sense to write an expression for AC because we've been given information about the vector AC and the vector BD, that they're equal. So let's investigate that. AC, if I smash together AB and BC, and we've got expressions for both of those. So I know AC would be A plus B. What about BD? BD, smash together BA and AD. Now, BA, they told us anything about, oh, well, they told us AB, didn't they? So that's the negative of A that we want. And AD, they told us was K times BC, but BC is equal to B, so that's K times B. All right. Well, the information we know is those vectors, their magnitude is equal. Okay, so yeah, they're equal, but that also means their square's equal. which then allows me to introduce the dot product, because when I've got magnitude squared, I can write it as AC dot AC equals BD dot BD. So let's do that. Now, left-hand side, we'll expand it out. It's sort of like a perfect square. You'll notice I didn't bother writing A dot A this time. I just went straight to magnitude of A squared. Yeah, it's usually okay to do that. But the middle one, of course, I still have to write as A dot B. Don't write it as AB. Remember, you're not multiplying. It's a dot product. So 2A dot B plus magnitude of B squared. Right-hand side, also a perfect square. So K is just a constant, so K squared. But magnitude of B squared minus 2 times K times B dot A plus magnitude of A squared. Now, let me look at what we're trying to get to. It has 2 lots of A dot B. Well, I've got 2 lots of A dot B in there. I've got some other things as well. Magnitude of B squared, yes, I've got that. Magnitude of A squared, though. Oh, but that's all right, because I've got magnitude of A squared on both sides, so that'll disappear. I can get rid of that easily. So, okay. What am I left with if I start grouping the things that I want? I wanted the A dot B. So if I group all the A dot B's together, I've got 2 lots of K plus 1. If I group the magnitudes of B squared together, I've got 1 minus K squared. We're almost there. 1 minus K squared is the difference of 2 squares. So I've got 1 minus K, 1 plus K. So I've got this common factor of 1 plus K. But importantly in this one, I can just divide by 1 plus K. Now, I know it's unusual to divide in an equation by a pronumeral, but you can do it if you know for certain that what you're dividing by is not equal to 0. Now, because K is a positive number, then I know 1 plus K can't equal 0, therefore I can divide by it. And I'm left with the expression that they wanted. So, that was last year's HSC. Okay, so we'll have a go at playing with some of these geometry proofs in 8D.